All right. Hello, everybody. Welcome back after our social hour. We have 2 more talks today, and so we're going to dive right into it. I'm super happy to introduce Kian Jones, who is the president of BitSoc here at Carleton. Kian's in his 4th year of the network technology major at Carleton under BIT. And so without further ado, I'll bring Kian on.
Hi. Hello, everyone. This is my first time using like a real fancy like streamer microphone, so forgive me if I accidentally drop a couple thanks to the 5 gifted or whatever, right? So today I wanted to do a little presentation about network tunneling because I just heard that a lot of CS students don't necessarily get a great background in networking, and I think network tunneling is an interesting application of networking that is appealing for a wider audience. It's like more interesting than just studying network itself. So a little bit about me. I'm in the BitNet program, network technology major, president of BitSoc. I've done some co-ops in the data science field, in cloud infrastructure engineering and network engineering. And finally, in July, I will be joining Facebook, aka Meta, full-time as a network engineer on the Facebook connectivity projects, which are basically like a bunch of projects to get more people on the internet so that Facebook can in turn get more users. A little bit of an overview of what we're going to talk about today. We're going to talk about key terms. We're going to dispel some typical misconceptions about VPNs and network tunnels. And we're going to talk about, how network tunnels work at different layers with some exceptions. So first misconception, right? VPNs are not secure. Okay. Now, you could argue that what we typically think of when we say VPN is an encrypted VPN. Sure. But I kind of want to just get in early at the start of this talk and just talk about that not all VPNs are secure. You may have other reasons to have a VPN rather than just for security and encrypting your traffic. So we have this concept of encapsulation as well as encryption. So you may just want to segregate certain traffic rather than encrypt it. So I want to talk about some of the misinformation that's online about VPNs. And maybe, yes, again, maybe this is just the colloquial use of the word VPN being synonymous or just known as an encrypted VPN. But a VPN, by definition, in our networking world, is not encrypted. A lot of stuff out here that I'm sure a lot of us more technical people probably know is not true, but like the masses are kind of being given this information about VPNs, which is not necessarily true. And maybe it's just marketing and trying to make it easier and more digestible for non-technical consumers. But encryption of IP address, that's just not true, right? Because how would you even forward traffic to an encrypted address if you didn't know what that address was? um, Encryption of logs, like that. I mean, having access to the logs is different than encrypting them, right? And everyone's seen those YouTubers who are like, oh, if you're at the coffee shop, they're going to be able to look at your traffic. It's like, where are you? Like, what are you doing that you're not using HTTPS on these websites to do like highly sensitive tasks? And then, just people online saying, you heard wrong. A VPN, there's no such thing as an unencrypted VPN. And you may be asking yourself, how does George Bale know this? Well, he lived in Miami. I just thought that was really funny. So encapsulation is not encryption. So VPNs always encapsulate traffic. However, sometimes they encrypt traffic, sometimes they don't. Examples of unencrypted VPN technologies are GRE, generic routing encapsulation, and IP in IP, or IPIP. And then encrypted, we have IPSec and TLS, or SSL. But, quick interlude. Just wanted to mention this fun fact. Split tunnel is basically like when you are on your company's VPN. Let's say you want to listen to Spotify while you're at work on your computer. I mean, this isn't like all VPNs. It's not a sure thing, but most VPNs or most VPN clients would offload non VPN traffic, for instance, your Spotify, to just like sending it through your regular network internet destined traffic. Whereas like it would take the traffic destined for the VPN network and send that through the VPN so that you're not overloading the VPN system, or so you're not like sending too much traffic through or whatever, or unnecessarily. I know a lot of these images are probably really scuffed, and that's just my fault because I use snipping tool. There's different types of tunnels. Again, I'm not sure how familiar a lot of you guys are with like the layers of a network, but we have the OSI model, right? And we talk about layer 1, layer 2, layer 3, which is like physical data link, network, layer 4, transport, TCP, right? UDP. And so I wanted to kind of talk about today layer 3 and layer 2 tunnels, which I think maybe don't get a lot of attention. I'm not going to talk about like the application layer TLS tunnel type stuff because frankly, I just don't know about it. And I don't want to misrepresent any information or mislead anyone. So not quickly, because this is the whole content of the presentation. So I don't know why I'm trying to race through it. But layer 3 VPNs. So when we talk about a layer 3 VPN or a layer 2 VPN or a layer X VPN encapsulates traffic that is of that layer. So a layer 3 VPN encapsulates layer 3 traffic. And if we're not super familiar with what layer 3 traffic is, that's like an IP packet is layer 3 traffic. Now, what's going to come up a couple times throughout the scope of this talk is maybe more archaic protocols that I want to use because that's how I know some of these concepts, and maybe I might not know the newer ones, and I just want to illustrate the point. So, for instance, AppleTalk, IPX, these are former super old competitors to IP, but overall IP won out the layer 3 race, right? And so that's what I mean by layer 3 traffic is any protocol operating at layer 3 of the OSI stack, or the OSI stack. So let's talk about why you would want to use a layer 3 VPN. That is, so imagine you have two networks, IP networks, that you want to connect as if they were directly connected, but they're actually geographically dispersed and have to transit, for instance, an ISP's backhaul network, well, you can't just like wire it up, a super long cable from Vancouver to Calgary. Well, I mean, you could run like a fiber cable that far, but what I'm saying is like you might not have the means to have a dedicated link between these two geographically disparate points of presence, we'll call them. So you can use a layer 3 VPN to encapsulate the traffic and have it appear as if they're directly connected. Another important point about layer 3 VPNs is they are point to multipoint, which means if you look at this diagram on the right, the lower one, you'll see the hub and spoke. So the spokes would be the point I'm trying to convey is that the tunnels are actually point to point, but they get kind of changed. So if remote office in the example is trying to communicate with remote office 3, pardon me, if remote office 1 is trying to communicate with remote office 3 over layer 3 VPN, that green line there, that spoke to spoke tunnel, is what it's going to logically believe that it is accessing, but really the traffic will be flowing through the spoke to hub, and then the hub to the other spoke. And then of course I wanted to illustrate, I added this top diagram to illustrate how that encapsulation kind of works. So in layer 3 VPNs, the layer 3 protocol in almost every case, right, IP or IPv6 as well, right, would be the payload of that packet. So that would be the data field in this diagram. The header and the trailer, that's what's encapsulating it, and that would be dependent on the type of layer 3 VPN, which is what we're about to talk about. So the first one that I just figured was the most basic is IP and IP. And what an IP and IP tunnel is literally you're just taking an IP packet and making it the payload of another IP packet. So there's no additional, we'll say, no additional protocol flags or anything, nothing new in the actual message. So if you look at this diagram, the little Christmassy one with the red and green, the actual IP packet remains the same. We're just adding another IP header to forward it differently than if we were to use the actual IP header. So this might be in the case of, let's say we have those two geographically disparate offices. We want to act as if they're the same, if they're just like adjacent networks, right? Well, maybe we have private addressing and that's not like a publicly routable IP address, right? That inner IP header. So we might need that outer IP header to explain how to forward that packet through the internet to reach the other office, for instance. Some pros and cons, IP is widely supported because it takes almost no vendor or implementation related, like the vendors don't have to do much additional implementation since it's just rerunning it through the IP stack. And it's very, very, it's the most efficient you could have for a very specific use case. And you'll understand that better in a few more slides, but that is to say that without adding extra, the use case is very limited in that it can only be used to carry IP packets in IP packets. But if that's what your use case is, then this is the most efficient solution. That's what I'm trying to say. So now IPSec, and IPSec is what you would think of as that traditional, it's one of the options for that, for what you would think is the encrypted VPN. And IPSec is actually very complicated. So the first thing you would do is you would go through IPIC phase 1. IPIC is Internet Key Exchange. And that sets up that first tunnel you see, that IPIC phase 1 tunnel in green on the right. And then that's kind of where ISACAMP, which is like, it's like Internet Security. Oh no, Internet Security Association Key Management Protocol or something like that. And so it's kind of like you're doing the asymmetric. It's like if you've ever looked at sending encrypted data, you do the asymmetric encryption, which is less efficient but more secure for sending, secure at all for sending data to the other node. And then once you've used the asymmetric encryption to send a symmetric encryption key, then you can use the more efficient symmetric encryption and decryption method to send all of your traffic. So if you had to do asymmetric encryption on everything, that would be super inefficient. So we use symmetric key encryption, which is shared after we have the IPIC phase 1 tunnel. And then we use the symmetric encryption key with the IPSec tunnel with the IPIC phase 2 tunnel, which is like in turn the IPSec tunnel. And one thing to mention here is you'll see at the top, building an IPSec tunnel pair, right? So by default, it's actually like a unidirectional tunnel. And to have bidirectional communication, you have to establish 2 tunnels, one going each way. And then another thing, IPSec is not inherently encrypted. So you can set up an IPSec tunnel that's not encrypted, and that's exactly what we've done, unless we enable technically unless we enable ESP, but let's get there in a sec, right? So is authentication header, and it enables authentication and integrity, if you're familiar with the CIA triad. And actually, I don't even think that's the CIA triad. But anyways, it enables authentication and integrity. However, it does not encrypt the data. So if you want encryption, you're going to have to use ESP, which is Encrypted Security Protocol, something like that. And that's going to add, some more headers and stuff. So to make it, it's going to encrypt the data and also add these headers, just like in the right diagram here where we have And so the use case for I should say, hold on one sec. We've got transport mode and tunnel mode. Transport mode is essentially just if you want to transfer the data, whereas tunnel mode, again, when we talk about the nuances of tunneling and network tunneling, I really want to get across that tunneling is when you encapsulate data. So if we're tunneling some traffic, we are changing the way that traffic would be routed by default, in that it would probably be dropped because it's a private address or something like that. So if you look at this diagram, when it's in tunnel mode, we're encapsulating it with a new IP header, which is presumably routable. And we're hiding that IP header, the inner IP header. And we're not really hiding it because it's and we're not actually encrypting it. We're just making sure that we can tell whether it's been changed, like by hashing and stuff like that. Okay. Generic routing encapsulation, GRE, is another protocol for doing that kind of tunneling we talked about in the first slide about IPIP, aka IPMIP. And the G in generic routing encapsulation stands for generic, and that's kind of the advantage over IP in IP, is that now we've added a field, we've added a header, and that header includes a protocol field, and that protocol field specifies which protocol is being carried inside that GRE packet. So that could be IPv4, IPv6, ARP. There's like a bunch of other protocol flags. These are just some examples. And so the GRE header adds 24 bytes to the IP packet. And you might be thinking like 24, like okay, that's nothing, right? But in some very specific cases, that's, necessary information. I also think, sorry, what I meant to say is that looking at the diagram, it also can fulfill that same function of connecting geographically separate areas, as if that they're, directly connected. And imagine in this case where we have the protocol field flag of ARP, where we're not just sending, regular IP traffic, but we can account for making an ARP request that has response across the that like internet WAN ISP backhaul to the other side of our um, seemingly connected connection. Quick interlude on MTU. If you don't know, MTU is maximum transmissible unit, maximum transmission unit. And here Newton's third law applies. So Newton's third law is every action has an equal opposite reaction. If you're adding headers and you're adding information about, to tell a tunnel endpoint about how to handle the traffic that's coming out of it, you're also going to have to adjust the amount of traffic that you can send through in one PDU, which is protocol datagram unit. So you could think of this as a packet or a frame, depending on the type of VPN you're running. So here's where we talked about earlier. So if you're adding just a regular IPIP header, so if you're adding an IPIP header, which is just another IP header around your existing IP header, that's 20 bytes. So here, when we add GRE, that's an additional 4 bytes. Okay. And that could matter, right? So that's why I was saying that IPIP for its purpose is the absolute most efficient. But for most intents and purposes, GRE is going to be efficient enough, right? Like that 4 bytes is not really going to break the bank for most people. Okay. Little MTU nerd interlude. Okay, now we talk about MPLS, which is like another way that you can do tunneling. And MPLS works at layer 2.5, they say, and we'll have more illustrations of that. But just a quick example is the protocol. I try and show what the PDU or protocol datagram unit looks like in each of these examples, just so you guys can get an understanding of like what exactly is going across the wire. And we see the MPLS header here is inserted between the layer 2 header and the IP packet, which we talked about, was the layer 3. So that's why it's kind of called layer 2.5, because it's a shim between 2 layers, or it can be. We'll talk about that in the next section. But one of the biggest use cases for MPLS is that it's underlay agnostic. So again, we talk about these archaic protocols and physical technologies. We have frame relay and ATM, which were 2 popular layer 2 protocols, and Ethernet has basically just replaced both of those, and it's just ubiquitous, and it's I hesitate to say an awesome protocol, but only because I think that sounds ridiculous as a sentence. But Ethernet has become like the de facto standard, and not many people use ATM or frame relay anymore. And yeah, I think I don't really remember why frame relay was discarded, but I think ATM was technically maybe more efficient, but too complicated, because you had to do a lot of like chunking, and each message, each MTU was maximum 53 bytes. So it became really a lot more processing heavy on the like routers and switches and stuff like that. Anyways, this is to say that certain ISPs, certain internet service providers may still run that older architecture or those older technologies, especially in certain less profitable areas. And they may choose to run MPLS because it allows them to forward traffic as if they were forwarding, or regardless of whatever that technology is. So the way if you look at the PDU outline there, is you can see that after we've dealt with the layer 2 header, we don't even touch the IP packet. So these devices in between these PE1, P, and PE2, these devices don't actually have to run IP. They don't have to be able to speak IP. They don't have to be able to understand IP as a protocol. They can just use the MPLS header to decide how to forward the packet without needing to understand the inner workings of whatever upper layer protocols. So MPLS works by having, there's kind of like two parts to it. So you have a signaling protocol. So the examples listed here are label distribution protocol, resource reservation protocol with traffic engineering extension, and multi-protocol border gateway protocol. Multi-protocol border gateway protocol. And if you're familiar with any of these protocols, but you're not familiar with MPLS, you might get a bit confused because you're thinking about them in the functions that they traditionally have. These protocols in this context have only the function of sharing information to set up tunnels. So MPLS works by, you might have guessed, I guess we've talked about the multi-protocol aspect of it. And now when we get to label switching, so MPLS works by sharing labels that correspond to tunnels, which are paths through the network between devices. So for instance, if you wanted to share from PE1 here to PE2 here in this diagram, you would have a label on PE1, on P and PE2, and that label corresponds to which tunnel to forward the packet through, or maybe not packet, protocol agnostic. And so LDP, label distribution protocol, distributes labels. Well, they all distribute labels. That's what I was trying to get at, is that they don't do what they traditionally have done, which is, well, besides the point. But they actually just share information about how tunnels should be configured through the network and how traffic should be forwarded through those tunnels. Then the forwarding protocol is what actually what actually works in the data plane to forward the traffic based on those labels that they see. So what makes MPLS appealing is that it's actually very efficient, because you're not doing any kinds of IP resolutions, you're not doing any lookups, right? You have one operation, and it's kind of like when you learn about like hash maps and why that's like a O of 1 access, right? Is that label that's maybe, let's say, 300,298 or whatever, right? That the label that the packet comes in with is not hash maps, but you basically hash it, and you have a 1-to-1 lookups. You immediately know the information that corresponds to the ingress label. The ingress label tells you, okay, where to forward it out and with what label to forward it out with. So if we see something come in on this P router here, and it has label X, we look up in our system, okay, X goes to this label and forwards out this port. So then there's a lot of more complicated implementations, but essentially in the basic sense, that MPLS label would be swapped for label Y, let's say. So X gets swapped for Y and forwarded out the port corresponding to Y. And so it's a very quick and efficient operation at each hop in the network along the traffic path. And there's like a bunch of other reasons for MPLS for MPLS and using tunnels everywhere. And I don't really have time to talk about all of that, but we're going to talk quickly about layer 2 tunnels, which are even more complicated. So if you've already checked out, that's probably okay. But so layer 2 traffic, or layer 2 VPNs, mean encapsulating layer 2 traffic. And I wrote here, this also means layer 3, because I don't want you being like, oh, layer 2 encapsulates layer 2 traffic, because it also encapsulates the layer 3 traffic within that layer 2 traffic, because layer 2 traffic carries layer 3 traffic, and in turn layer 4, 5, 6, 7. And this can be used to emulate as if, let's say, the two geographically separate areas are part of the same LAN. So as if maybe there isn't even a router between them. And that might be needed for certain older technologies that don't operate in the same way. It might be needed for, they use layer 2 VPN sometimes with data centers as like a data center interconnect. They have like, as if the data centers are part of the same layer 2 segment. Yeah, and then of course here on the right we have the concept of like a point to point, which is, if you've ever heard of if you've ever heard of the term leased lines, it's kind of like a virtual leased line, they call it, or aka pseudo wire, and that's just a point to point layer 2 VPN. And then if you want like a point to multi-point layer 2 VPN, that would be, well, in Nokia terms, a VPLS. I'm not sure what there's like HVPLS, and then there's like, which is a hierarchical VPLS. And then what we're going to talk about in a second is like other kinds of layer 2 VPNs. So you guys might not believe this. I actually made that diagram on the top myself. You probably can't even believe that, but I made that. And I made it because I couldn't really find anything that really fit my needs online, even though I plagiarized like almost all the images here today. And I wanted to talk about MPLS applied to layer 2 VPNs as a really kind of to round out the concept of MPLS being used as a very versatile protocol. And so the way that works here is, if you look at the diagram on the bottom, you'll see the regular packet from customer A is like, you know, an IP packet with a layer 2 frame around it. Maybe that's IP in Ethernet, right? IPv4 in Ethernet. We don't need to know the specifics, but then we get tagged with this purple MPLS label. Ignore the purple, ignore why there's 2 for now, because it's just like out of the scope of this talk. But that whole IP layer 2, we'll say PDU, that frame with its IP information and with its layer 4, 5, 6, 7 information, is intact the entire way through until it reaches customer A CE2 on the other side. The only thing, this layer 2, this layer 2 here, underneath those purple MPLS tags, is the layer 2. It's the layer 2 technology of R1, R2, R3. So customer 1 may be sending with their layer 2 being Ethernet, but if you're an ISP who's still on, let's say, frame relay or ATM, like we talked about earlier, you're still going to have, you can still run that traffic, encapsulate it underneath, and send it with your network access, network media access. What am I trying to say? With your layer 2 data link layer technology that you use to communicate from R1 to R2, for instance, without any change. Well, of course, you have to configure MPLS. And then you see that comes out preserved, untouched on the other side. And I wanted to illustrate this with this diagram that I now realize is probably redundant because it's essentially the same here. But the value I think that I added is having the color all the way around to show that, this Ethernet header is encapsulating this IP packet entirely. This underlay L2 header is also encapsulating everything entirely. Yes. Finally, I want to talk about layer 2 overlays. So you have what's called the EVPN, which is an Ethernet VPN, which is just like emulates Ethernet over a VPN, also using MPBGP, and then VXLAN, which is virtual extensible LAN, and that's a technology that interconnects, again, geographically disparate, or not even geographically, but it could be just be like, they're right next to each other, but they're physically different networks, as if it's one single layer 2 segment. So you can look here and you see this VTEP, and that's basically your MAC table, if you've studied anything like that before, which is just a mapping of MAC addresses to ports. So you kind of send in some traffic with, and depending on where that traffic is destined or which MAC address, your VTEP like translates that into a tunnel endpoint kind of thing. And thank you for coming to my talk today. I hope I didn't go too long over, and thank you for coming. I hope you enjoyed. I hope that was interesting.
Hello. Can you hear me?
Yeah.
All right. Yeah, Kian, this was super cool. So I mean, you said right off the bat, CS students might not know so much about networking, and like my knowledge is like there are layers and there's stuff that's less than 5, but we have HTTP up here, and so why would I care about this? And so this was a super cool talk. I think I've done some networking stuff in the sense of like when I do UDP and TCP for gaming, I kind of think about like, oh, like what does MTU mean, and like why does this matter for like our larger packets or whatever. But it was really cool seeing stuff at this level with the VPN. I'm taking a look here for if there's any questions in chat, and I don't know if I see too many. But actually, one question I did have myself.
Probably because I explained it so well that
Oh,
nobody has any
exactly.
questions about it.
Yeah. And so what I was wondering is when you start at Meta, can we start like you're doing networking at Meta, right?
Yeah. So I'm working on so Facebook connectivity is a portfolio of projects which are to get more people online. So they're kind of, I hate to beat a dead horse, but like they're disruptive or innovative in a way that allows smaller ISPs, for instance, to get to lower the barrier to entry for smaller ISPs to get into the space for providing network access to people. And I in turn work on this team that basically is like kind of a DevOps team, or we develop tools to help people deploy the solutions easier, or we develop tools to test the products before they come out.
Nice. Yeah, that's super cool because yeah, I was sort of wondering like when we hear about a lot of the theory here, how does that apply to like what you actually do in practice at jobs? And so yeah, it's kind of like a cool overview of that.
Yeah, it's very much like a ISP backend infrastructure type thing where you're presumably you could be selling like user access to this backhaul network over, you might be a backhaul network provider as your job, and you sell to other networking companies like maybe like those that provide wireless access. You might sell them access to your backhaul infrastructure, and you might have a different customer ID associated with different tunnels so that you can easier like track how much usage people are doing, and like charge them differently depending, or treat their traffic differently depending on how much they're paying, kind of thing.
Yeah, interesting.
QoS.
I do like I do some video game work where I host a server that a lot of people play on, and we host a server in Germany. And I know that since it's hosted in Germany, there's like people who can't connect to it as well. And I've heard people say like it has to do with like peering, it has to do with all this networking stuff, and I don't really understand that too much. So like for me, as a computer science person who knows like a lot of like how code works and like how data sort of moves, or how data is, but not really how it moves around. How would you recommend someone like me can get like more into this world of networking and like understand more of these like lower level topics?
I would say it's kind of cliche, but like following one of like the cert tracks like CCNA is pretty well. They just revamped it, so it might be better now. But if you just follow maybe the kind of if you look at what they ask for in this test, and then you kind of read up on some of those things, I think that would go a long way. There's people on YouTube who explain all sorts of this stuff better than I do. There's one guy in particular, like Keith Barker or something, and he does a really good job. So shout out
Yeah,
to him.
okay. Nice. Yeah, so I'll take a look at some of these recommendations, maybe
I guess
check
what I'm
some out.
trying to get across is like if it's part of a certification track, then people there's many resources because people want to learn it to get the certification track.
Yeah, okay. Well, awesome. I think we're going to come back in just a few minutes with Matt, who's going to give us a talk on Kafka. But Kian, thank you so much for being here and giving us a little bit of a look into this networking side of tech a little bit.
Cool.
Yeah,
Thank
so
you for
thank you.
having me. No
Cheers.
problem.